Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR NET, GATE, NT exam, PhD exam, SET exam, Jest, Tifr, IIT-Jam exam and other exams related to physical science. Okay, so also guys, I would request the people who haven't subscribed my channel yet, please subscribe my channel. And this is the lecture number 8 of quantum mechanics, in which we are going to which I'm going to discuss the postulates of quantum mechanics. We are going to study the postulates of quantum mechanics. Okay, so I'm going to start. Okay guys, so if you want to explain, if you want to describe the state of a particle, or state of classical particle, I mean, so in that case, if we know the position and momentum of particle, so we can easily describe the state of particle in classical mechanics. Okay, but and also we can calculate any other physical quantity relevant to the system uh, in terms of momentum and position. In similar way, if you want to explain or describe any quantum mechanical system or any particle in quantum mechanics, the state of any particle in quantum mechanics or the state of quantum mechanical system, we use the postulates of quantum mechanics. Okay, so so and those with the help of those postulates we can easily explain the quantum mechanical system. Okay, so I'm going to write as well, so that you can make notes of it also. Okay, so now it is postulates of quantum mechanics. Okay, postulates of quantum mechanics. Quantum mechanics, which we are going to study. Okay, very important guys. Okay, so I'll write it and explain also. So the formalism of quantum mechanics, the formalism of quantum mechanics, quantum mechanics formalism of quantum mechanics is based on a number of postulates, a number of postulates. Okay, these are very important postulates. With the help of that, we can easily describe any quantum mechanical system. Okay, so the formalism of quantum mechanics is based on the number of postulates. Okay, so these postulates these postulates these postulates are in turn based on a wide range of wide range of experimental observation. Okay, experimental observations. Okay, So this is the formulation of quantum mechanics is based on the number of postulates. So there are number of postulates. There are 5 postulates which we will study. Okay, and these postulates are based on wide range of experimental observation. So we did lots of experiments on the basis of those experimental observation, and the postulates of quantum mechanics is given. Okay. Second point is the postulates. The postulates the postulates cannot be derived. Cannot be derived. Okay. Cannot be derived. They result from experiment. Okay. They result they result they result from experiment. So we cannot derive it, guys. Okay, these are the postulates which we cannot derive, and because they but they result from the experiment. Okay, so we got it by we got those postulates by experiment. Okay. Okay. They represent this is about the postulates of quantum mechanics. Okay, they represents they represents the minimal set of the minimal minimal set of minimal set of assumptions minimum set of assumptions needed needed to develop to develop the theory of quantum mechanics. Develop the theory of quantum mechanics. Okay. Okay, so they represent the minimal set of assumptions, okay, to develop the theory of quantum mechanics. Okay, these are set of assumptions. Okay, next point. their validity their validity their validity cannot be determined cannot be determined so we cannot determine their validity. Okay, determine directly. Okay, directly directly only an indirect only an indirect only an indirect inferential statement inferential statements inferential statement is possible. Okay, so it's saying their validity, we cannot directly validate it. Okay, so we can validate it indirectly. Okay, only an indirect inferential statement is possible. Inferential statement means uh, which can be proved based on the evidence. Okay, so directly we cannot determine. So indirectly we can determine it. Okay, next point. And guys, also I would like to tell you that if you are studying my courses, so you don't need the separate preparation for interview, guys, because I'm writing everything and explaining everything. So my course is not going to help you to clear the written exam, but also it is going to help to clear the interview. Okay, PhD interview. So so you can make notes of it as well. That's why I'm writing all these things. Okay, next point is the quantum theory. Okay, quantum theory not only works, not not only not only works, but works extremely well. Okay, works extremely well, works extremely well. And yeah, so the quantum theory works extremely well. Okay, uh, and this represents this represents this represents its experimental justification. Experimental justification. Okay, experimental justification. Okay, so the quantum theory works extremely well, and this represents its experimental justification. Okay, so these postulates work extremely well. Okay, so now I'm going to write the postulates. There are 5 postulates, and I'm going to write one by one. So this is about the postulates of quantum mechanics. Okay, so now I will write those 5 postulates. The number first postulate is state of a system. Okay, state of a state of a system state of a system. This is postulate number 1. Let me check whether my internet working fine. Okay. Yes, it's working fine. Okay, the first postulate is state of system. So so I'll explain the state of system. Okay, the quantum mechanical state of system. Okay, the state of any physical system the state of any physical system is specified is is specified is specified at each time at each time at each time t by the state vector, by a state vector, by a state vector psi, cat psi, which is function of t, okay, in in a Hilbert space, in a Hilbert space, in a Hilbert space, okay, and psi, which is function of t, psi, which is function of t, contains all needed information, all needed information, all needed information, all needed information about the system. About the system. Okay. So, so here the psi, which is the wave function, okay, this represents the state of the system, okay, at any time t, okay, this represents the state of system, okay, this is the psi is the wave function, okay, this represents the state of any system, and with the help of the wave function, this wave function contains all the information about the system, okay. So if you know the wave function of the system, so we can get all the information about, we can know all the information about the system, okay. So this psi, the cat state psi, this represents the state of the system in quantum mechanics, okay. I hope you understand it, it's very easy. So psi is the wave function which tells the state of any system, okay, in quantum mechanics. Next postulate, that is observable and operator. Observable and operator, observable and operator, okay. Observable and operator. Okay, so now what is observable and what is operator, which I'm going to discuss here, okay. First I'll write this statement, that is to every physically measurable quantity, to every physically measurable quantity, to every physically measurable quantity A called is any measurable physical quantity, okay, called an observable and observable or dynamical variable, or dynamical variable, okay. So to every physically measured quantity A, called every physical quantity which is measurable, Okay, if you talk about in quantum system, like kinetic energy is a physical quantity, okay, and this is measurable, right? uh, Called observable, so we call it observable or dynamical variable. So that can be anything like in a system, that is that can be momentum, position, okay, pressure, so all physical quantity which are measurable, right? They are called observable or dynamic variable, so we call it dynamic variable or observable. So in quantum mechanics we call it observable, okay, or dynamic. And okay, so this is about the observable, okay, called observable or dynamic variable. There corresponds variable, there there corresponds there corresponds a linear Hermitian operator, a linear Hermitian operator, a linear Hermitian operator, linear Hermitian operator, a cap, okay, a cap. So if there is a if observable is a, then the Hermitian operator is a cap, okay, whose eigenvalues whose eigenvalues whose eigenvalues sorry, whose eigenvectors whose eigenvectors whose eigenvectors form a complete basis, form a complete basis, okay, form a complete basis, okay. So this is the second postulate, observable and operator. To every physically measurable quantity a, every physically measurable quantity a called an observable or dynamic variable, okay, and there corresponds a linear Hermitian operator a whose eigenvectors form a complete basis. So suppose if we take example of kinetic energy, right? Kinetic energy is k, that is the observable. And what is the operator for kinetic energy? The operator for kinetic energy is minus h cut square upon 2m del square, right? This is the operator, okay. So for any of, for example, this is the observable. So for this observable there is a operator like this. There is a operator, and which is Hermitian, operator, okay, means whose eigenvalues are real, okay. That's what this second postulate is saying, okay. I hope you understand the second postulate, guys. Similarly, if we talk about momentum, P is the momentum, then operator is minus I h cut del upon del x. This is operator. This is this is the observable or dynamic variable, okay. Well, this is the second postulate. Now we are going to explain third postulate, okay. Every postulate is important, guys. Okay, the third postulate is measurements and eigenvalues of operator, okay. measurements measurements and measurements and eigenvalues measurements and eigenvalues of of operator. Okay, measurements and eigenvalues of operator. Okay, this is the third postulate, measurements and eigenvalues of operator. So that we are going to discuss now. Okay, so this is the measurement of an operator. The measurement the measurement of an observable A. Okay, a may be represented. So how to measure any observable A? Okay, so measurement of an observable A represented may be represented may be represented formally by by the action of operator A, by the action of by the by the action of by the action of operator A on a state vector on a state vector on a state vector on a state vector state vector psi t, state vector psi, which is function of t, state vector psi. Okay, so the measurement of observable A may be represented formally by the action of A on a state vector psi. It will get clarified. Uh, I will clarify it for you. Okay, after I will write this statement. Okay, so okay, the only possible result of such a measurement, the only possible result, only possible result only possible result of such a measurement of such a measurement is one of the is measurement is one of the is one of the possible result of one of the eigenvalue one of the eigenvalue 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 an. Okay, eigenvalue an eigenvalue eigenvalue an which are real, okay, which are real, one of the eigenvalue n, okay, which are real of the operator a, operator operator a, okay, of the operator a, if the result of a measurement, if the result of a measurement of a result of a measurement of a on a state on a state psi, which is function of t, on a state psi is an, okay, if the result of a measurement of a on a state psi t is an, the state of the system, the state of the system state of the system immediately after measurement, state of the system immediately after the measurement changes to psi n, okay. So this is saying like if you want to measure a like this, okay, this is the vector a, if you operate like this with psi, this function of t, this is going to give an an, this is the eigenvector, eigenvalue, and psi t, right? This is what it is saying, okay. So here this is an is the eigenvalues, any one of the eigenvalues of the operator a, okay. Now what this sentence is saying, if the result of a measurement of a on a state psi t is an, the state of the system immediately after the measurement changes to psi n. So it means what it's saying, a so this becomes operating a with psi t, function of t, this is going to be an psi n, okay. This is what it is saying, okay. So an is then the state of the system immediately after measurement changes to psi n. So this changes to psi n, this is what it is saying, okay. This is the one this is saying, this complete sentence, okay, this one. And where an is the value of an is psi n psi t product, okay, this one is very important, okay. So this is what this state is saying. So if you operate this with the eigen function, okay, with this wave function, okay, so this becomes like this, an is the eigen one of the eigenvalues of the operator, okay. and it immediately this becomes psi n, okay, after measurement. So this is the one, and where value of an is psi n psi t, product of psi n psi t. Okay, I hope you understood, guys. So this is the postulate number 3rd. Now the postulate number 4, and this is probabilistic outcome of measurement. Okay, probabilistic probabilistic outcome of measurement of probabilistic outcome of measurement. Okay, well, so this is, and this is the first case of this is for discrete spectra. So we are talking about discrete spectra, discrete spectra. Okay, discrete spectra, this is the case. So this is when measuring an observable A, when measuring an observable A of a system, this is A is the observable, right, physical quantity, measurable physical quantity of a system in a state psi, the probability of probability of obtaining one of the non-degenerate eigenvalues an of the corresponding operator A is given by Pn An. This is going to be psi n eigen function. Okay, psi mod square upon product of psi n psi. Okay, or we can write this value is an, right, an mod square upon psi n psi. This one, because this value an is this psi n psi. Okay, this I have already explained here. This an is psi n psi t. Okay, so this is what, so for discrete, so it is saying, okay, when measuring an observable A of system, when we are measuring the observable A of the system in state psi, the probability, so we are getting probability of obtaining one of the non-degenerate eigenvalues. Okay, one of the non-degenerate eigenvalue, yeah, probability of getting one of the non-degenerate eigenvalue of the corresponding operator A is given by this. Okay, for getting an, this is eigenvalue, one of the eigenvalue is going to be psi n psi mod square mod of psi n psi mod square of psi n psi upon psi n psi. Okay, so this is wave function and this is the eigen function. Okay, well, so this is the one, and next point is, okay, so where psi n is the eigenstate, is the eigenstate or eigenfunction, eigenstate of a operator A, with operator is denoted by a cap. Okay, a cap with eigenvalue, with eigenvalue an. Okay, okay, so this is eigenvalue and this is eigen state, okay, or eigenvector. Okay, this is the one. And in also, if it's if eigenvalue is, if, next point is, if the eigenvalue eigenvalue an, okay, any one of the eigenvalue, okay, an is m degenerate, so it's not it's m degenerate. Okay, it has degeneracy m. Okay, and degenerate in that case, the probability of obtaining the eigen value an is going to be sigma j equal to 1 to m. Okay, and this value is going to be psi n, which is j, psi n j psi mod square upon psi psi. Okay, this is the one, psi psi. Okay, psi psi, and or we can write it like this: sigma j equal to 1 to m anj mod square upon psi psi. Okay, this one. So this is the case of degeneracy, if it if eigenvalue is degenerate, so and the degeneracy is m. Okay, next point. The act of measurement, the act of measurement changes to state, changes to the state changes to the state of the system from psi to psi n. Okay, to psi n, which I have already explained. Okay, the act of measurement changes the state. As we measured the eigenvalue, then psi n will get changed into, psi will change into, the wave function will get changed into psi n, that is wave function, eigen function. Okay, or eigenvector. Next, if the system is already if the system is already is already in an eigenstate in an eigenstate psi n of a measurement of a psi n of psi n of operator a measurement of a measurement of a yields with certainty the corresponding eigenvalue an, okay, that is a psi n equal to an psi n, okay. So this is the what it's saying, yeah. If the system is already in eigenstate psi n, so system is already in eigenstate psi n of operator a, the measurement of a yields certainty the corresponding eigenvalue, okay, yields with certainty, okay, yields with certainty the corresponding eigenvalue an, okay, that is an psi n equal to a psi n equal to an psi n, okay. This is the fourth postulate, first part of fourth postulate, and the second part of fourth postulate is for continuous spectra. Second part is continuous spectra. For continuous spectra, okay, this is for continuous spectra. For continuous spectra the probability is going to be in the range, okay, in between a to a plus dA is going to be, probability is going to be, so this is the case of continuous spectra. Del A is going to be psi, which is function of A mod square upon psi, okay. This one, or similarly, for example, the probability density of finding particle, probability density of finding a particle between x to x plus dx, is going to be del p, which is function of x upon del x. This is going to be psi, which is function of x mod square upon psi psi. Okay, so this is the fourth postulates, second part of fourth postulates. Now the fifth postulates, last postulates, the evolution, the time evolution of system, the time evolution of a system. Time evolution of a system. Okay, time evolution of a system. This is the time evolution of the system the time evolution of the state, time evolution of the state of the state vector psi, which is function of t, of a system is governed by the time dependent Schrödinger equation. Okay, that is given by Schrödinger equation, that is, we know I h cut del upon del t with psi, which is function of t. This is going to be equal to h psi, which is function of t. Okay, this is the time dependent Schrödinger equation. Okay, where h is the Hamiltonian operator, the Hamiltonian operator corresponding to the total energy of system, of the system. Okay, so this is the fifth postulate, that is the time evolution of the state vector psi t of the system is governed by the Schrödinger time dependent equation, which is this. Okay, this is the discussed now. Okay, so these are the 5 postulates, very important, guys. And so now we can easily explain any system using these postulates. Okay, so these postulates are very important postulates of quantum mechanics. Okay, to explain any quantum mechanical system. Okay, so guys, I think I'm going to solve one question for it. Okay, and then we will wrap it up. Okay, so this question is asked in 2011, I believe. This is CSIR net question. So one question we are going to do. This is the question number 1. This is, suppose the Hamiltonian of a conservative system. Suppose Hamiltonian of a conservative system in classical mechanics in classical mechanics is H equal to omega phi p phi, okay, where omega is a constant omega is a constant and phi and p phi are and phi and p phi are the are generalized are the generalized coordinate and its conjugate momentum. Generalized coordinate and its conjugate momentum in polar coordinate respectively. The corresponding Hamiltonian Hamiltonian in the quantum representation is corresponding Hamiltonian in quantum representation is, okay. Options are option number A, I h cut omega phi del upon del phi minus 1 by 2. Option B is I h cut omega phi del upon del phi plus half. Option C is iota h cut omega phi del upon del phi plus 1. And option D is minus iota h cut omega into phi del upon del phi plus half. Okay, this is the question. The question is, suppose the Hamiltonian of conservative system in classical mechanics, the Hamiltonian is given, okay, where omega is the constant, phi and p phi are the generalized coordinate and its conjugate momentum in polar coordinate respectively. The corresponding Hamiltonian in quantum representation is, okay. Okay, so this we need to find out. Very simple question. So we have Hamiltonian given in quantum mechanics. Now we need to find out Hamiltonian operator in quantum mechanics. Okay, so this is given solution. classical mechanics, the Hamiltonian for classical mechanics is given omega phi p phi. Okay, so now we have to uh, find out the Hamiltonian in quantum mechanics, that is Hamilton operator. Okay, we need to find out. So how we are going to find it? This is going to be, we can write this like this. This is going to be 1 by 2 omega phi p phi plus p phi phi. We can write it, right? This we can write it. Okay, so we have done half, and this one, if we solve it, this going to be, this is going to give the same. Okay, so we can write this as this. Okay, so this is going to be 1 by 2 omega phi p phi plus 1 by 2 omega p phi phi. Okay, now we have to find out the operator, the Hamiltonian quantum mechanics representation, right? For that, we'll take psi on both sides, the wave function. So this is going to be psi equal to 1 by 2 omega 1 by 2 omega, and this is going to be phi p phi psi plus p phi phi psi. We have taken psi both side. Okay, so now this is going to be h psi is going to be 1 by 2 omega and phi p phi. So this is, we have taken psi, so this is going to be operator now, and okay, because we have to find it in quantum mechanics. Okay, so this is going to be phi, and this value we know, minus iota h cut del upon del phi. This we know, right? Since p phi equal to minus iota h cut, this is operator in quantum mechanics, del phi, right? So we have written here, plus this is going to be p phi, the value of p phi will write minus iota h cut del upon del phi, and this is going to be phi psi. Okay, so this is going to be h cut psi, the h psi, h is operator, it's omega, and what we are going to do is, we are going to take minus iota h cut common, minus iota h cut omega by 2 will be the common, and this is going to be phi del upon del phi. There is psi as well. Okay, psi. Okay, and this is going to be, there are two functions. So first function phi del psi on del phi, plus second function psi del phi upon del phi, right? This we know. So this is going to be h cut psi is going to be this one. Iota h cut is going to be common. This is minus iota h cut omega by 2, h cut omega by 2, and this is going to be, these two will get added, right? 2 phi del psi upon del phi, and this is plus psi, because this value is going to be 1. Okay, so this one, now psi will remove it, so it is going to be operator h is going to be, will remove psi from both sides. Okay, this is going to be minus iota h cut omega by 2 phi del upon del phi plus 1. Okay, 2 will take 2 here, 2 will take inside, so this is going to be operator h cut h pi H cap is going to be iota h cut omega by 2. Sorry, we have taken 2 inside, so this is going to be phi del upon del phi plus 1 by 2. Okay, this is the answer, guys. So in quantum mechanics, the operator h is going to be this. And which option is matching? Option number D, right? This one, iota h cut del phi upon phi del upon del phi plus half. Okay, this one. This is the answer, guys. Okay, so 1 by 2, yeah, this is the answer. Okay, so well, guys, I'm going to stop here now, and after this class I'm going to take one more class of quantum mechanics, where we are going to study the particle in one dimensional infinite potential. Okay, both symmetric potential and asymmetric potential. That's what we are going to discuss, and then we'll solve questions which were asked in Jest and Jam and Gate, right? Because I'm also taking quantum mechanics PYQ class separately. Okay, so that's why I will solve only Gate in lecture class. In theory class of quantum mechanics, I will solve questions which were asked in Jest, IIT-Jam Gate examination. Okay, on an NT examination, and not I will not solve PYQ which were asked in CSIR net, because I'm already I'm taking a separate class for PYQs of CSIR net. Okay, so I think I have taken 7 lectures so far for CSIR net PYQ. Okay, tomorrow I will take the next lecture for CSIR net PYQ. Okay, well, guys, so thank you so much for watching my lecture, and also I would request the people who haven't subscribed my channel, please subscribe my channel. Okay, and watch my lectures uh, which are free of charges and which are going to help you to crack exams related to physical science. Okay, guys, thank you so much. Bye now.